Now let's consider this equation, the equation set. If we want to solve it, actually the first command is not necessary. If we use quotation mark, it will assume that these two are symbolic variables. So the first one is not accurate. This one is not necessary. We can remove that one if you need. And you can express the first equation and then the second equation. Of course, you can use 0.75, something like that, no problem using it. So we can declare the two equations and then code the solve function so that we can find the x and the y. So let's see what are the x and y obtained. We see that we have vector x and a vector y. Each contains 6 components, and 2 of which are real numbers. The other 4 are in contact conjugates. So that is why when we're using graphical method, we only find 2 solutions. This one composes a pair of solutions, and this one with the other real solution composes another pair of solutions. So in this case, we can find all the 6 pairs of solutions to the original equation. So now let's verify the result, the solution, and find the accuracy of the solution. And I can use for evaluate, EVAL for evaluate. For string, we can use the word evaluate to find the value. Or for expression, we can use double or VPA to find the solution. It should give the consistent result. So if we are using this command to evaluate the errors in the equation, we see that the errors are very small, much more smaller than we use double precision algorithms. Almost zero. So the errors are almost zero. So we can use solve command to solve, we call it polynomial type equations. Let's consider a more complicated one. Suppose there is an equation with 3 variables, x, y, and z. And we are not lucky in this equation because we cannot find the easy form in the previous example, like something like this. We cannot find this kind of method to simplify the result and transform it into a polynomial equation by hand. So we must rely on computers to do the work. And we can express the 3 equations and code them and separate them by commas, and then we can code the solve function. And finally we can return x, y, and z as the solution to the equation. In this way we can solve the original equations, and finally we shall find the result. It may take some time for this example because there are too many solutions. And then we can verify the result by coding a command like this, and then we can evaluate. In fact, we do not have to use the eval function. We can just use double. It should be double should be okay. I'm not quite sure. I don't think we have to use it. I don't think we have to use the eval command, because it is already a symbolic expression, so we can use double. That should be okay. And then we can find an error in the solutions. So these are the solutions. So we can check. For this equation, we may have 27 solutions in all, which means that x, y, and z are 27 by 1 column vectors. So we can have 27 solutions for this equation. And now let's check the accuracy of the solution. That is to substitute the solution back to the original equation and see what happens. And again, we see that the solution, the accuracy is very high. And this method also works if we substitute one of the equations by a form like this. In the previous equation, we only see that they are independent powers of x, y, and z. If we have a mixed term, this method also works. And also, if the polynomials are denominators, we can also solve it in the same way. And we can use this command. We do not have to change the form of it. We do not have to multiply them by cube or something. So we can just express the equation itself in an easy way like this, and we can find the solution to it. And then we can verify the result. And I'm not going to demonstrate this part in class, so you can run the demonstration later on your own computer. It may take, I think, less than 1 minute to find all the solutions to the problem. And you can immediately verify the results. And the norm of the error matrix should be something like 10 to the power of minus 28, 39. It will be very accurate, much more accurate than the one we used, than the double precision scheme we obtained. And this the solve function also works for this kind of equations. If there are extra variables a and b in the equation, we can also solve the problem with the solve function. It should be something like this. However, for this kind of equations, you must be very careful, because they only deal with simple equations. For complicated equations, because therefore high degree equations, there is a very famous Abel-Rodney theorem states that for the equation of order 5 or higher, there is no analytical solutions to it. So up to now, it seems that the solve function is quite powerful. It can be used to solve any kind of equations. But in fact, it is not as powerful as we have expected. There are limitations in the solution in this algorithm, because it is only suitable for polynomial kind of equations. For other kind of equations, we can still use that solution, but there are limitations. We cannot find all the possible solutions. So this kind of solution only applies to polynomial type of equations. Now let's consider the example again.